Okay, here's warm-up 5.4. All right, we're going to be simplifying this big fraction here. When I have a big fraction that is raised to a negative exponent, the first thing I like to do is to flip the fraction upside down, and then this will become a positive 2 exponent. There are definitely different ways you could do this. You could start distributing the negative 2 to all the pieces, or raising everything to the negative second, or you could start simplifying the fraction first. But what I'm going to do is just flip everything as it is first. So let's see. Okay, that was from the denominator there, right? I just wrote it exactly as it is, and then this comes from the original numerator. Okay, and this is all now going to be raised to the positive second. So now that changes this exponent out there to positive. Okay, now I could start again raising everything to the second power, but I think what I'm going to do is start simplifying the fraction. So 8 over 24, for example, would reduce to 1/3. So I'm going to have a 3 down there. You don't really need to write the 1 in the numerator because there will be other things there. Okay, everything that has a negative exponent, I'm going to use the stairs. So I'm going to pull this into the denominator, so it'll become an x to the first in the denominator, and I'll pull this one up. And there are different ways to go about this too. So I'm just circling the pieces that have a negative exponent because I want to write everything with positive exponents. So let's see, this x to the third would end up here, and this x to the first would be down there. And this is, let's see, I had the y squared down here. Now I'm also going to have y to the third down here. I have the z that's staying up there, and now I'm also going to have another z up there. And then this is all still raised to the second power. Okay, so let's continue to simplify here. So with the x to the third over x, one of the x's will cancel. That means I'll be left with x squared in the numerator. And then this 3 will still be down here. For the z, z times z is z squared. And then y squared times y to the third would be y to the fifth. It would be 5y's all multiplied together. Okay, and this is all still raised to the second power. So I still want to square everything. So I'm going to square the x squared. I'm going to square the z squared. But I'm also going to square the denominator. I'm going to square the 3 and the y to the fifth. So that means in the numerator I'll have x to the fourth, z to the fourth, and then I'll have 9y to the 10th. And that is as far as we can go simplifying that. Okay, a lot of different routes you can take, but there's only one destination that you should reach, and this is what it looks like. Okay, next problem. This is not considered simplified because we have a radical in the denominator, so we need to rationalize the denominator. What I see often is that people will multiply by root 3 over root 3, which isn't a bad idea. That's what we would do if we had something like this, just 4 over root 3, we'd multiply by root 3 over root 3. But if you do that here, then you'd have to distribute in the denominator, and we'd still have a radical in the denominator. So that's not going to work. What we want to do instead is to multiply by the conjugate of the denominator when we've got something this format. So the conjugate of 2 plus 3 would be 2 minus root 3. The conjugate, you just change the sign of the radical. Okay, and whatever I do to the denominator, I want to do to the numerator so that I'm really just multiplying by 1. I'm not changing the value of this function, just changing its form. Okay, whoops, I'm going to distribute the 4 over here, put my arrow the wrong way there. Okay, so this is going to give me, here I'll work down here, this is going to give me 8 minus 4 root 3. In the denominator, I'm going to want to FOIL this, so because I've got a binomial times another binomial. First, outer, inner, last. First, 2 times 2 is 4. Outer, 2 times negative root 3 is going to be negative 2 root 3. Inner, root 3 times 2 would be positive 2 root 3. And then last, and I feel like for some reason the most mistakes get made with the last, I've got positive root 3 times negative root 3. Well, a positive times a negative will come out negative. And root 3 times root 3, I can put the 3's under the same roof, so that would be root 9, like so. Okay. Now I still have radicals in the denominator, but Those ones are gone because they're opposites. They're going to add up to nothing, okay? And then when I look at the square root of 9, that's actually 3, right? So now I've got 8 minus 4 root 3 over 4 minus 3. And I can simplify 4 minus 3 to 1. So that means that this is 8 minus 4 root 3. And I've rationalized the denominator, right? No more radical in the denominator, okay? All right, next problem. So I want to simplify this. So I'm going to use simple radical form. So I first want to see if I have like terms. These don't appear to be like terms because there's different radicands, different things under the radical. But hang on, this isn't in simple radical form. This piece is, right? There's no twins under the, well, the way I do it is with twins. There's no, you can't break down the 3 any farther. So this is in simple radical form. But I can break down 12. So I'm just thinking of a multiplication problem where the answer is 12. I'm using integers. So, 4 times 3 would be 12, or 2 times 2 times 3. And then I do have twins there. So when you have twins, they make a break for it. One gets out, one doesn't. So one of those 2's will get out of the radical. And now since there's a 5 and a 2 outside, I multiply them together. Now I've got 10 root 3 plus 9 root 3, and those are like terms now. So 10 of those plus 9 of those, that means I have 19 of those being root 3's, okay? All right, last problem. We're going to graph this radical function. So you have to know a little bit about what a radical function looks like. It's going to look sort of like a swoosh. This, since I have this negative, that means my swoosh is going to open down to the right like that, okay? That's from this negative. All right, so I'm going to first find the vertex. This point is the vertex. To find the x-coordinate, I'm going to take the radicand and set it equal to 0. And then I'll solve for x by adding 3 to both sides. So that's going to be the x-coordinate of my vertex. And then the y is whatever is added or subtracted to the end of the radical like that. So my vertex then is going to be the point 3, 1. Okay? So I'm going to plot that. That's going to stay put once I get it in place. So 3, 1 is right here. Okay? And I've got a swoosh that's going to open down to the right. So you have to know what the parent graph looks like. Okay? So I'm going to, this is going to stay put. I'm going to plot what I call my ghost points. I'm going to imagine what this would look like if there's no stretch or compression. There is going to be a stretch or compression from the 2, but I'm going to pretend there isn't for a second. So the parent graph opening down, I'd go down 1 to the right 1 like that, and then from the vertex down 2 to the right 4. So if the 2 wasn't there, if this was just this equation without the 2, that's what it would look like, a swoosh going down like that. But I do have the 2, okay? And I'm looking at the 2 by itself because the negative just makes this open downwards, right? So I'm just looking at the 2 itself, and I've got to deal with that. So first thing I would think of is a parabola. So I'm kind of thinking this in my head. Well, what would, if I had 2x squared, would that make my parabola wider or narrower? So if this is the original parabola, my parent graph, that would actually make it narrower, right? So that means I'm going to have, I'm thinking narrow. Okay, so then I would think, is this a horizontal or a vertical change? And if the 2's inside multiplying the x directly, then it's a horizontal change. So if I had 2x minus 3 inside, that would be a horizontal change. It's not inside, it's outside, so that means this is a vertical change. Okay? So then I have to put these two things together to figure out if it's going to be a vertical stretch or a vertical compression. So if you think about if this is the parent graph that I just marked, well, to make this narrower, if I'm only moving these points, well, let's use these actually. If I'm only moving these points vertically, that means they're only moving up or down. I do actually want to think about a parabola, the original parabola, because this kind of looks like a sideways parabola, which makes things a little confusing. But if I have these, and these points can only move up or down, and I want this to look narrower, well, I'd have to move these points up. I'd have to move them up like that, and that would give me a narrower parabola. If I move them down, the vertex is gonna stay put. It's gonna look like it's getting squished, and it'll look wider. So this is gonna be a vertical stretch then. So that means I'm gonna take these points and move them vertically, okay? So I'm moving them vertically away from the vertex. So since this is 2, that means I'm going to double their vertical distance. So right now this first point is 1 unit below the vertex. I want to double that, so now it's 2 units below the vertex. This is 2 units below, so I want to double that, and that puts me down there. And now I've got what I need. There is my radical function, and it doesn't really look narrower because it's half of a parabola, but if you think about an original, if you think about a parabola, then you can think wider and narrower to help you figure out if it's a stretch or compression. Okay. All right, that's it for this warm-up, and I'll see you next time.